In this video, we're going to be looking at the importance of the FDE cycle, how the FDE cycle impacts registers, and how data is basically sent between registers and also fetched from memory, and how we use buses. So there's quite a lot of technical information in this presentation. Before watching it, I strongly suggest you watch the video on components for CPU, because that will help explain what a bus is, and it'll explain what opcode and operand is, and what machine code instructions are, etc, etc. So this really is the spec point. As you can see, it's kind of overlapping with components a little bit, because you can't really fully understand the CPU without actually having both those parts. Okay, so we're going to look at it primarily, but before we go on to that, we really need to recall what we mean by register, because we're going to be using registers a lot in this presentation, so it's important to remember. So what can you recall from the last topic? What do you know about registers? What is a register? So the temporary memory located in the CPU, used during the execution of instructions. So when I'm running instructions on the CPU, I'm going to be making use of these registers. They run at the same speed as the CPU, so then we're not going to get that problem we get with the memory and the von Neumann bottleneck. Their size is going to be based on the CPU itself. So if it's a 64-bit CPU, we have 64-bit registers. And we're going to learn about some special purpose registers in this presentation specifically, but there are also some general purpose ones which are free to be used during the execution of machine code instructions, and when you're writing your code or compiling it into machine code, those registers can be used freely. So, also recall, one of the registers we did look in some detail at was the accumulator ACC, which is used by the arithmetic logic units to store the results of arithmetic operations or logic operations, and also stored and used by input and outputs. It also is used during the execution of instructions such as adding as part of the instruction as well. So we looked at that last presentation, I'm not going to spend so much time on it. So what we're going to be looking at is how instructions are fetched. We're not necessarily going to be looking in any detail actually in decoding or executing. We're just going to be effectively brushing over that side of it, making the assumption they are decoded and executed. So really, when we say the FDE cycle and we want detail on the FDE cycle, what we're really talking about is fetching. Okay, so fetching is key. It's going to do all three of these actions at the same time, but on different instructions. Now, in A2, we'll be looking at something called pipelining, but effectively, the FDE cycle is an example of pipelining, where we have different instructions all doing something different. Okay, so while I'm fetching one instruction, I'm executing the last instruction I've just fetched. Okay, that way we get a little bit of efficiency, so I don't have to wait for instructions to be executed before I start fetching the next one. So there's a little bit of concurrency there. So when we say fetch, it's really important that we understand what we mean by this. So when I say fetch, I'm talking about fetching something from RAM or cache. Now, we're not going to make a distinction between RAM and cache. We're just going to say RAM from this point onwards. Okay, but in technical terms, we're actually talking about cache. So it always goes to cache first, and then it goes to RAM. That's part of it is all controlled through the memory unit, through the cache manager. It's not really something we worry about when we're talking about fetching. Okay, so although technically we are going to be fetching from cache, for this point onwards, just think of it as RAM. So any given fetch, we have no idea whether it's a cache or not, so we don't worry about it. We just assume it's going to come. And when we fetch, we're going to be doing one of the following. We're going to be either an instruction to code and execute, so I'm going to fetch an instruction, or I'm going to be fetching some data needed by instruction in order to finish executing. Okay, so we don't always fetch instructions, sometimes it might be data as well. So fetching will only access single instruction data once. So this is one of the things which is, it's a bit of an issue with the von Neumann architecture, specifically the bottleneck, is that I can only fetch one thing at once. Okay, so I can fetch one instruction, one bit of data. So I can get, if I've got a 32-bit processor, 4 bytes, if I have 64-bit, 8 bytes, but that's all I can get at once. Okay, so we're really limited by the speed of memory, not by the CPU. Okay, so that's it's one of the core drawbacks. So instructions data must be fetched into CPU before I can process. So it really is a big bottleneck. So we're going to be focusing in on fetch now. In order to do the fetch, we've got 3 key registers which play a massive role, okay? So there is a 4th register which we're going to introduce in a bit, which is a CIR, but for now we're going to focus on these 3. So the program counter, or PC, will store the address of the next instruction to be fetched. Effectively, this is kind of the look ahead. It's always pointing to the instruction I'm about to go and get. The MAR is going to be storing the address of the instruction I'm currently fetching. So that is the thing that's going to be sent over the address bus, and the MDR is going to store the result of a fetch. So when I actually have got something from memory, it's going to go straight to the MDR. So the FDE cycle makes use of 4 key registers. We've mentioned 3 of them, and the 4th one I kind of just hinted towards. What you need to know for the exam is the purpose of each register and what they store. Okay, that's really important. You understand the difference of what they're storing as well. Okay. Thankfully, it's quite easy to understand because the name kind of gives it away. So memory address register, it stores addresses. Okay, so it does give itself away. How and when they change, so at what points in the FDE cycle are they changing, how certain instructions might change the FDE cycle. So there are 2 types of instruction where the FDE cycle starts to change, and how buses are used. Okay. In order to fully understand the FDE cycle, we're going to be making use of an example. Now, this example is written in Listman Computer. This is something we're going to be covering in detail in AS. However, you might have already been introduced to it in GCE as well. It makes use of 4 commands. IMP, this will basically get an input and store it in the accumulator. Add will take the operand, the number 7, add it to the accumulator. Out is going to display the contents, and halt will stop processing. Now, just a little caveat, I'm aware in Little Man Computer 7 will be a mailbox. I'm going to treat it as an actual number because it makes the FDE cycle a bit simpler. So let's actually see how this works. So initially, the program counter is going to have 0, the address 0. So it's going to be pointing to the first instruction I need to fetch, in this case, input. The first thing that happens in the FDE cycle, I take the contents of the program counter and I basically copy it over to the memory address register. I then will add 1 to the PC. Now the PC always points to the next instruction I'm about to fetch, not the instruction I'm currently fetching. This is why it always increments immediately after it copies. Now, a little caveat, when I say +1, I really mean point to the next instruction. Now, if my instructions are 1 byte long, it's going to +1. If my instructions are 4 bytes long, it's going to be +4. Okay, it's depending on the size of the instruction. So, the program counter increments for 1, and it's been copied over to the memory address register. The next thing I need to do is do a fetch. So, the location 0 has the instruction input, so that's going to be copied over to the MDR, or basically fetched. Okay, just kind of linking to something we're going to be looking at in a bit. It's going to be coming via the data bus. So during the fetch, the instruction data points to the MLR, is copied to the MDR, as just said. When we do a fetch, in this case I'm fetching the instruction, but it could be data as well. Okay, so regardless of the instruction data, the process is always the same. I use the MAR to go into RAM. Whatever's in that location gets copied and saved into the MDR. Once that fetch has occurred, we need to start executing. Now, here, what I've done is I've copied the instruction I'm about to execute into the CR. You can see that has this instruction here. The MDR is fetching the next instruction. So this second instruction, you can see, is now inside the MDR. My MAR is pointing to that, but my program counter, you can see, it's actually pointing to the second one. Sorry, this got a little bit messy. But you can see there's every register will have a different value. Okay, program counter always the instruction I'm about to fetch next. The MAR is storing the instruction I've just fetched, or I'm about to fetch, and the MDR stores the result of the fetch. The CR is going to then store the instruction I'm executing at that moment in time. So now's a good time to actually talk about the CIR. So one instruction is fetch and only instructions. Okay, this is one of the key things about its name, instruction. It never has data, always instructions. So it's going to have the instruction copied over to it, which will then be decoded and executed. If this happens at the end of the clock cycle, so once the code instruction is finished, okay, and the end of the clock cycle happens, we then basically copy everything over it. So you can think of it all like a timing kind of thing. So every beat, the contents of MDR is copied over the CIR unless something different is happening, and I'll talk about that difference in a moment. As an instruction, the CIR has been executed, the next instruction is always being fetched. So we're executing one instruction while fetching the next. Okay, that's always happening. That gives us a little bit of parallelism, and we call it pipelining. So to summarise the FDE cycle, the program counter is copied to MR first. The PC is incremented by one instruction. Data is then fetched into the MDR or instruction, depending on what we're doing at the moment of time. The MDR is copied to CIR if it's an instruction, and then the instruction is decoded and executed from the CIR. As one instruction is being decoded and executed, we're always fetching the next. Two caveats to this, and which we're going to be looking at in a moment. The cycle can be altered and changed if a second fetch is needed when executing instruction, i.e. if the instruction's operand is an address, because that means I need to do another fetch. Or it's a jump command, and we'll talk about jumps in a moment. So it's worth summarising the key registers. Program counter always points to the next instruction to be processed. Will be incremented each FDE cycle by one instruction, and if a jump command occurs, then the program counter is going to be updated, and we'll look at that in detail in a moment. So the memory address register will contain the address of the code instruction that needs to be fetched, or it could be the address of some data that needs to be fetched, depending on if an extra fetch is needed when executing the current instruction. The result of the fetch is always placed in the memory data register, regardless if that is an instruction or data. The memory address register updated if the current instruction is required an extra fetch. So if an extra fetch is needed, it will store the address in the memory address register. The memory data register holds the data instruction resulting from the current fetch. If instruction is going to be sent over to CIR in the next cycle. If it's data, then that data is going to be used with the instruction in the CIR currently in order to execute. The current instruction register instructions are copied into the CIR for decode and execution. If the instruction has more data to be fetched, then it will update the the memory address register is updated during execution of the instruction. If the instruction is a jump, then the program counter is going to be updated. So it's a time to pause. In order to make your notes good on this, make sure you describe the four key registers in detail, and then make sure you write down the algorithm for the FDE cycle, and also make sure what parts of the FDE cycle is used for each register. There are two situations where the FDE cycle might change. The first one is when you need to do additional fetch. The second one is when a jump command is executed. So we're going to look at both those two scenarios in a bit more detail now. So let's say we are running or executing an instruction which requires an additional fetch. The operand of the instruction will contain a memory address which will point to the data we need to fetch. So let's look at a scenario how this might work out. So consider we've got an 8-bit CPU and our opcode contains 3 bits and our operand has 5 bits. So in this scenario, our operand can only store 5 bits. So that means the largest number we can store is going to be 15, because the biggest number you can store in 5 bytes is 15. Let's consider this scenario. So here I've got an instruction. The first instruction is add, and that is the opcode. Okay, you can see that's taking up 3 bits, 0, 1, and 2. My operand is taking up 5 bits, and I'm storing this binary number. Now I've written out in binary just to kind of show you in a bit more detail. So it's going to add the thing from address 8, the data from address 8. Okay, so this is an address, it's address 8, because that's going to be 1, 2, 4, 8, and 16. It's actually quite hard to write with a mouse. So that's going to be pointing at address 8, and the address 8 contains this number here, which is number 30. So in order to execute this, I will need to do an additional fetch. Okay. So first of all, the address of the add instruction is loaded into the memory address register, then the instruction is fetched into MDR. So this is address 0, the instruction add is loaded into the MDR, then that's copied to the CIR and executed. Now, unfortunately, because that is an address and not a data, it needs to do an additional fetch. So it will take the opcode, which is this part, and copy it into the memory address register. Okay? And this only happens if it is an address. It will then fetch that data into the MDR, okay, which now has the value 30. And once that fetch has completed, the instruction add can then execute, okay, because it's now got the 2 bits information it needs. Okay, so it's now going to add 30 to the accumulator, and then that instruction is complete. So in order to do double fetch, if an instruction contains a memory address in the operand, then I'll need to do additional fetch. Okay, if it's got data in the operand, we don't need to do that. Okay, in order to do double fetch, the operand, which contains an address, will be copied to the memory address register. We then fetch the data into the MDR, and then finally the instruction can execute with both the CR and the MDR. Now, jump commands are basically how the CPU handles iteration, selection, and procedures, i.e. loops, if statements, and functions. Okay, so essentially what happens with a jump command, it will jump to a different part of the program. Okay, so anytime we have a command which will change the flow of a program, we are effectively going to be using a jump in assembly. Okay, so in order to jump to another part of the program, we effectively need to change the program counter. Okay, because remember the program counter is going to be pointed to the next instruction to fetch. The problem with fetching is we're assuming we're going to run commands one after another in sequence. When I do a jump command, I'm changing that sequence. Okay, so whatever has already been fetched is going to be lost. So we update the program counter rather than the MAR. So if I execute jump commands, the operand, which will contain the address of the instruction I'm going to be jumping to, is copied over to the PC, and then we start the FDE cycle again. Okay, so one of the key problems with a jump command is that any fetches I've done up to that point, so remember while I'm executing one command, I fetch the other one, that extra fetch I've done is going to be lost. So we lose the benefits of the pipeline. So this slide contains a summary. Okay, it's a very clear summary. However, one thing I would suggest is make sure you fully understand the double fetch and the jump scenarios. To finish off, it's good to do a few exam-style questions. So the first question, describe what register may change as an instruction is decoded and executed in CR. Okay, for that question, the idea here is to talk about what registers can be updated, and that is going to be the MAR and the PC. MAR if it's double fetch, PC if it's jump. Describe the role of the PC. Okay, you need to introduce to this question the jumps. Okay, because it also stores the result of a jump. And finally, explain how the registers involved in the FDE cycle change during the fetch of a single instruction. Again, you want to explain the FDE cycle and explain how the registers are changing, but also talk about those two scenarios, the double fetch and jumps. Now, to finish off, we just need to very quickly look at how the buses and FDE cycle work together. Okay, so one thing to be really clear is that when data is passed between registers, so for example, when I copy the program counter to the MAR, we don't use any buses at all. Okay, they're not actually going outside the CPU. So the only time we ever use a bus is if data is going in or out of the CPU. Okay, because all the registers inside the CPU, we don't need buses. So when data is fetched into the MDR, that's the scenario where I'm going to use a bus. Okay, so essentially any data which comes from outside the CPU will use these buses. So the idea is this. So a fetch will first send a control signal via the control bus and an address via the address bus to RAM. Okay, the address bus will contain the contents of the MAR. So in this scenario, we've got the MAR here, which contains 5, and that's sent down the address bus to RAM. The control bus will basically also send the instruction that we want to do, in this case loading whatever is in that RAM at that point. Then the data gets sent back via the data bus, okay, and gets stored inside the MDR.